Hey everyone, welcome back to the channel and to a new lesson in our astronomy unit. In today's lesson we are going to be discussing the solar system. So briefly, let's talk about what the solar system is and how we can sort of think about it before we dive into it. Now I'm sure lots of you have had at least some discussion about the solar system before, either with me or with another science teacher, or just between yourselves, discussions of the planets and the moon and the sun and things like that. They come up not super frequently, but they do come up in everybody's life every now and again, especially with events like solar eclipses or lunar eclipses or things like that. The subject of the solar system does come up every now and then. So I'm sure you guys are at least somewhat familiar with it, but basically before we dive into the rest of our astronomy unit, I want to go through some of the nitty-gritty details of the solar system, not to throw a bunch of numbers your way. I know we saw some stuff on dealing with really big and really small numbers using scientific notation in the first lesson of the astronomy unit, and that might be useful later on if we're talking about the masses of very large objects or the distances between objects. In this lesson, I don't really want to throw a bunch of numbers at you. Instead, I want to talk about sort of some of the highlights of the solar system, and then in a future lesson, if you guys are interested, or just if I feel like it's necessary, then I can make another video that deals with more of the numbers to give you more of a feel of what exactly we're talking about in this unit. But anyway, for now, suffice it to say that we can think of the solar system as our sort of cosmic family, or maybe our neighborhood in space. The universe is a really big place, and in the next few lessons we're going to explore different aspects of the universe at different scales. So we'll look at relatively small stuff like planets and stars in our solar system, and then we'll look at bigger things like galaxies. So in this lesson, we're just going to talk about the stuff that's contained within our solar system, which you can see on the screen. Some of the highlights of the things that are within our solar system include the 8 major planets. Some of you might argue that that number should be 9, but we're going to talk about that later on in this lesson, I promise. But however you'd like to say it, 8 or 9, major planets, as well as some dwarf planets, which have, of course, been sort of at the forefront of astronomy news for the general public. Maybe not so much these days, but 10, 15 years ago it was a huge deal. And then obviously lots of asteroids and comets that capture the imagination of the public all the time, with things like Halley's Comet, or in popular movies and TV shows. It's not very difficult to write a movie or show or story that uses the threat of an asteroid impact or something like that as one of its main plot points. We've also talked about the possibility of asteroid impacts being the culprits of the extinction of the dinosaurs. So it's not like asteroids and comets are only talked about in an astronomy context. They show up in other areas of science and just of pop culture as well. So we'll talk a little bit about them. We're not going to focus too much on the asteroids and comets because obviously the stars of the show within the solar system are, well, the star, which is the sun, and the 8 major planets, as well as one particular dwarf planet, and I'm sure you all know what I'm talking about. We're going to get to all of that a little bit later in this lesson. So let's dive in. Now, you might have seen pictures like this in the past of diagrams trying to depict what the solar system kind of looks like. Either they're trying to show what it actually looks like, or they're just trying to show a pretty picture of all the planets all at the same time. So in the picture that you see on the left here, we've got a drawing that's got the sun and the 8 major planets. And then the picture on the right is definitely not trying to show the planets in their orbits or anything like that. It's just showing the planets in order from top to bottom. So it looks like we've got Mercury here, and then Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. With regards to this planet, Uranus, nowadays I tend to say Uranus around certain people. The name that comes most naturally to me is Uranus, but obviously people find that really funny. So you might find that I flip-flop between the two pronunciations. You feel free to call it whatever you want. Just I don't care if you find the name a little funny. That's okay. Everybody does. But just make sure that you're not letting that sort of prevent you from learning all the other cool stuff that there is to learn about the planet itself and about the rest of the planets. But yeah, so that's those are two popular examples of the kinds of pictures that you might see of the solar system. And I'm showing this because I'm going to show a couple of somewhat more accurate, quote unquote, pictures of what the solar system would look like. And I'm going to do that just so that you kind of appreciate how hard it can be to actually draw like an accurate representation of the solar system. So obviously these two are really good at showing in the first one, the sun and the 8 planets, and in the second one, the 8 planets as well as Earth's moon is this one right here. And these diagrams are a little bit misleading because they don't represent the sizes of the planets very well relative to one another, and they also don't represent the distances between the planets very well. So we're going to look at a couple of pictures like that as well. But before we jump into that, just here are a couple more examples of the kinds of pictures that you might see or might have seen of the solar system. This one on the left, which has like all the planets sitting on some sort of surface, does a better job of representing the difference in the sizes. So you can see that, you know, here's Earth right here, this pretty small one when you think about it compared to the rest of the planets, especially these 4 large ones. This is Jupiter here, Saturn, Uranus, and Neptune. And then these are the 4 small ones down here, the 4 rocky planets in the solar system. We're going to talk about them all in a little bit, but you can start to appreciate already just how big space is when you compare Earth in size to the 4 big boys on the block, which are these 4 planets up here. And as for this picture on the right, I have no idea what's going on here. It's just a mishmash of the planets in orbits that go kind of all over the place. Earth has a bunch of clouds floating out into space and a moon that doesn't really look anything like the moon. I have no idea what's going on here. And even just trying to follow the order is confusing enough of the planets. This picture is just an example of like what can go wrong if you're trying to teach students about like the planets and the order of the planets and things like that. But that's okay. Don't worry about that too much. So here is a more accurate representation of the planets in the solar system. Now we are going to talk about the planets in order, going from closest to the sun all the way out to the other end of the solar system. So you'll notice that in this picture and the couple of the previous ones and the picture after this, that I don't actually have the names of the planets right on there, but I am going to go through the planets sort of one at a time. This is a picture of the planet, this is its name, this is how you spell it in case you haven't seen it spelled out before, and we're going to look at all of them. So if you guys want to build a list, if you don't already have a list, that might be good. But that's just, I've intentionally left the names out just so that I make sure that you guys are paying attention in some way. So you're going to have to keep track of the order of the planets as we go through this. But here you can see in this picture we've got the planets of the solar system plus tiny Pluto over on the end there. And what we have is in this picture the sizes of the planets and the sun, which is this big yellow thing on the left. They are accurate relative to one another. So again, we can see that Earth is not very large, and then the big boys on the block are definitely the big boys on the block. They're very, very large in comparison to Earth, right? So this is one of the 2 big things that makes it difficult to draw a good picture of the solar system is that the variation in the sizes of the planets, so the difference between the biggest one and the smallest one, is so huge that it's kind of hard to draw them all in a way that doesn't make you just kind of forget about the tiny one over here and Pluto over there. The tiny one over here being Mercury. Also Mars is quite small, and Pluto over on the other end is also very small. Like if you were to just look at this picture from a distance, you would basically just see these four, and only upon closer inspection would you notice that there's actually more stuff in the picture. So this is one of the things that makes it difficult to draw a nice accurate picture of the solar system. Here's the other thing that makes it difficult to draw an accurate picture of the solar system. In this one, it says distances accurate. So the previous slide had the sizes of the planets accurate relative to one another. In this one, the sizes of the planets, just looking at the picture, it looks like the sizes are like okay-ish if you compare the size of one planet to another, but if you're comparing the size of the planet to the distance like on the screen, they would all just be tiny dots. So they would be much smaller than what you see on the screen. So the sizes of the planets are all kind of wonky here, but the distances are accurate here. So this all the way on this left edge, if hopefully you can see it, there's this tiny yellow sliver. That's one tiny part of the sun. And then the four smaller planets, so Mercury, Venus, Earth, and Mars are all in here. I don't even know if you guys could see them, especially if you're sitting at a desk and not directly in front of the screen. There are four small dots around here. Those are the four small planets. Then we've got the asteroid belt in the middle, which is a collection of basically space junk, and we'll talk about that a little bit later as well. And then we've got the four larger planets. We've got Jupiter here, Saturn here, Uranus here, and Neptune here, and then somewhere on the end is Pluto. And if I'm honest with you, on my computer screen I can't even see it. I could see it when I pasted the image here, and maybe I can see it on my second screen where I've got the presentation projected, but like honestly it's very small. I don't even know if I can see it on this, but that gives you a rough idea of the distances between the planets, is that they're not all equally spaced, and the planets aren't all roughly the same size, like we saw in that picture back near the beginning where all the planets were kind of lined up next to one another. Sure, there were some that were a little bit bigger, a little bit smaller, but in the sort of more common pictures that you might see or that might be shown in a classroom somewhere, tend to show the planets as being roughly similar in size and roughly evenly spaced apart. And what this image is trying to get across is that that is absolutely not true. So now let's dive into a closer examination of the planets in the solar system. So this slide here has a nicer, larger image of the inner planets of the solar system. Here, the sizes of the planets compared to one another are represented pretty well, but obviously they're not this close to each other in actual space. So these are the four inner planets. This one over here is Mercury. This one is Venus. Here is our good old Earth. And this is Mars over on the right. Now, you might notice that Venus and Earth are very similar in size. And it's true, they are very similar in size to one another. They're very similar in gravitational pull as well. Like if you're standing on the surface of Venus, it's not going to feel very different from standing on the surface of Earth. You guys might have seen video clips of astronauts on the moon, and they do this kind of like hop walk thing. And that's because of the reduced gravity on the surface of the moon, that they can tell that, you know, everything is like 6 times lighter than it should be. And it kind of makes them walk that way. And it's different on all the planets, but between Earth and Venus, that gravitational pull that you would feel on the surface is not particularly different from one to the other. Earth has a slightly stronger gravitational pull. It's slightly more massive as a planet, and so it's slightly larger and it's got a slightly stronger pull. But other than that, it's pretty similar. well, like sort of in the grand scheme of things, it's pretty similar in terms of how big it is. But when we look at pictures of Venus, you'll see that the two planets could almost not be more different from one another. But anyway, let's dive into a little discussion on the inner planets first. So I don't want to give you guys like a ton of numbers and a whole bunch of information that like memorize this because you're going to be tested on. I'm not trying to do anything like that because I feel like if I just ask you to memorize a bunch of numbers, that's the way of teaching astronomy that would make it boring. And so what I'm really trying to do in this lesson is I'm giving you a little bit of information. I'm giving you a few numbers in case you find them interesting. I'm not going to ask you to memorize a bunch of numbers. I'm just going to ask you to keep some kind of general information in your minds. And when it comes time for a test, I will let you know the kinds of questions I'm thinking of asking you. Yeah, so here are some of the things that you should remember about the innermost planets of the solar system. So we've got closest to the sun, we've got Mercury. You can see these planets are listed in order: Mercury, then Venus, then Earth, then Mars. So first things first, the order is good to know. But secondly, they've got some common traits. So one of the big ones being that they're mostly composed of rock and metal. So basically you could think of it as they're composed of rocks, like the kinds of rocks you find outside. And some of the rocks will have metallic compounds within them, or they're made out of metals like iron and nickel. Like in the case of Earth, iron and nickel are two of the primary elements that you would find in the core of the planets, down in the center of the planet. And so that's generally the case for all four planets in the inner solar system, is that they tend to be made out of things like metallic elements, and basically they're giant clumps of rock. That's what they are. And for that reason, you can also refer to them as the rocky planets because they're made of rock. Fairly straightforward. Or you could refer to them by their somewhat more professional name, which is the terrestrial planets. And one other thing that you've already seen from the pictures that we saw earlier is that they tend to be quite small, at least in comparison to the larger planets in the solar system, which we'll talk about in a little bit as well. Now you'll see at the bottom I've got this table of like the planet, the length of a day on that planet, and the length of a year on that planet. So just a couple of brief comments. I'm not going to ask you to memorize the length of the day. That's just there in case you happen to find it interesting. I, for one, when I started learning about astronomy, I would have been about 6 or 7 years old, and I had this book called Solar System, and it had this kind of a table on, like 5 or 7 pages in, and it had every planet and how long a day is and how long a year is, and I found those numbers so fascinating. I wasn't looking for patterns, though I am going to point you in the direction of a pattern in a second, but I just found it so interesting. I loved learning about it. I loved trying to memorize the length of a day to the planet, and I tried to imagine, it's like, what would it be like if that's how long a day was? So like, for example, if I lived on Mercury, one day would be equivalent to 59 days on Earth. And that's the other thing I wanted to clarify, is when I say Earth days, I mean the number of days that would pass on Earth is the same as the time it would take for one day to pass on whatever planet we're looking at. So in the case of Mercury, 59 Earth days would have to go by in order for one day to go by on Mercury. So that's for the planet to turn around once on its axis. So let me see if I can draw this for you. So basically you've got a planet like this, and it's got its like North Pole and South Pole, and the sun is somewhere over here, and the planet spins like this on its axis. So it rotates, like a fidget spinner but a ball, right? And so that rotation period is the length of a day, and the revolution period, the time it takes to orbit the sun. So the whole planet moves around the sun. You know, if this was the sun, then the whole planet would go around and then come back, is the time it takes for 1 year to pass. So hopefully you guys already knew that, but you never know. Sometimes it's good to clarify those kinds of things. But anyway, so here's the length of a day, just in case you happen to find that that stuff interesting. As for the length of a year, one thing I'd like to point out, just as you look at the table here and the table for the remaining planets in the solar system, is you'll notice that the length of the year gets longer as we continue through the solar system. So as the planets get farther and farther away from the sun, the years take longer to complete. Each year is longer on a planet that's progressively farther away from the sun. And just one absolutely last tiny point that I find tremendously interesting, but I basically just want to clarify that it's not a typo. Yes, a day on Venus is longer than a year on Venus. So that's cool. And I found that very interesting. My dad told me that when I was like 5 maybe, and it absolutely blew my mind. But yeah, that's like one of my favorite like solar system trivia facts, is that a year on Venus is shorter than a day on Venus. So that's pretty cool. It's also fun that the length of a day on Mars is only ever so slightly longer than a day on Earth. That's probably pure coincidence, but it's really cool. Anyway, what would an astronomy class be without pretty pictures of things in space? So I've got a few pictures. We're just going to look at a couple of pictures of each of the planets, and we'll hop into the discussion on the outer planets after that, the big four that we saw at the beginning. So here's a picture of Mercury. Not much to say about it. I'm not going to go into details of what exactly we're seeing on all of them, but basically all these marks on the surface of Mercury are impact craters. So basically space junk, asteroids, and basically tiny rocks, tiny chunks of rock and metal and maybe ice have throughout history smashed into the surface of Mercury and left these marks. And this is a reasonably common occurrence, maybe not so much now, but definitely at the early stages of the solar system. It was very common for the planets to be bombarded with these basically pieces of space junk. And if you're wondering why Earth's surface doesn't look like this, the short answer is basically two parts combined. One, we have an atmosphere which helps protect the surface from being bombarded by all these pieces of rock because they basically burn up in the atmosphere. And the second reason is that the Earth's crust, the Earth's surface, basically gets recycled over the course of millions and billions of years. So any craters that do form eventually kind of get smoothed out as the planet recycles its own surface. That kind of activity we don't really see on Mercury. So if you had something smash into the surface of Mercury, like one of these over here, for example, and you had it smash into Mercury like 3 billion years ago, that mark is still there because the crust is not recycling itself, and there's no atmosphere that would have, protected the planet against that impact in the first place. So here are two pictures of Venus. No, it's not two giant balls standing next to one another in space. No, this one here is what Venus would actually look like if you were to fly close to it. It's got a very, very thick, dense cloud cover full of poisonous gases, so that's fun. And then if you removed those gases, this is what the surface of Venus would basically look like. So if you were flying by Venus, but you removed its atmosphere, you removed its cloud cover, or you had some like special like X-ray goggles or something that let you look through the cloud cover at the surface, this is basically what the planet would look like. So you can see that even though it's, it's reasonably similar in size, and it's the closest planet in the solar system to Earth, if you look at like, the average distance from the sun, Sure, it's got those kinds of similarities, and for that reason, people call it Earth's twin. But when you look at this surface, it's kind of not very welcoming compared to the, the blue, green, white surface that we see of Earth. So, as much as it might be called Earth's twin, it's more like Earth's evil twin sister, rather than just a regular twin. So, there you go. There's a picture of Venus that you might not have seen before. And here's a picture of Earth and the Moon. Just for fun, I've kind of switched up. Instead of showing you a picture of somebody standing on the Earth and the Moon in the sky, I've shown you a picture taken from the Moon of the Earth. And you can see the Earth floating out in space. Again, there's the blue and white that we can see really easily of Earth from space, with obviously some different colors when you spot a continent on the surface. So this is Earth and the Moon. I don't think there's a whole lot that needs to be said there. You might notice that the surface of the Moon looks reasonably similar to what we saw on Mercury, obviously just a lot more zoomed in. And the Moon is similar in the sense of not having an atmosphere to protect it from these impacts, and not recycling its outer layers to smooth out those impact craters once they are left on the surface. So the surface of the Moon and the surface of Mercury do have some resemblance, basically because they're both missing the things that would protect them from having a bunch of crater marks on their surfaces. And here is a picture of Mars, the planet, on the left, as it would be seen from space. And here is a picture of the planet from its surface. So one of the really fascinating things about Mars is that we've, in recent decades, but even to this day, we send spacecraft, robotic spacecraft, out to Mars to study the planet. So some things would study the planet from in orbit, so without actually landing on it, they just go around and around and around the planet. And then others that actually land and drive across the surface and leave tire tracks and collect rock samples. And the purpose of that, especially in recent years, has just been to try and learn more about the history of Mars, the geology of Mars. What's the ground surface made out of? What's the soil type? I don't really want to call it soil per se, but what's the stuff on the surface of Mars made of? Does it have the kinds of things that you might expect to see a living organism feed off of, or a living organism made out of, or anything like that? Any of those like organic compounds? They're looking for that stuff, looking for signs of water, looking for signs of life. And so far, the signs of life thing is not really it's not really coming to fruition so far on Mars, but it's definitely an exciting prospect to see this era of space exploration unfold like at the present. This is something that's happening like these days while you guys are in school. And it's been going on for a couple of decades, but it's a really exciting time to be able to witness these things as they happen. And so I find it really fascinating that we can sit here in a classroom and look at a picture of Mars and see that this is what the surface of Mars actually looks like, and this sky is not Earth's sky, it's the sky that you would see if you were on the surface of Mars. Like, it's just mind-blowing to me that this isn't like an artist's rendition of what it might look like. This is what it actually looks like. So I find that really cool. Now, before we keep going with our discussion on the rest of the planets, let's talk a bit about the asteroid belt and the Kuiper belt. So basically, in simple terms, these are both regions of space junk, so debris, tiny chunks of matter, of rock or ice or something that are left over from the formation of the planets and the moons that we see in the solar system today. So the planets would have started out, maybe I'll make another lesson at some point, or like a mini lesson that talks about like the early days of the solar system and how it formed. But basically, you would have had a baby sun, young sun that's just formed, and just this massive mess of debris of basically a giant like disk, so like a big circle of basically like dust and like tiny like like pebbles basically. And over time they would crash into one another or get close to one another, and through their gravitational pull, you'd have the dust clump up into pebbles, and the pebbles clump up into stones, and the stones clump up into rocks, and the rocks clump up into boulders, and they would get bigger and bigger and bigger until you got a few that got bigger than everything else, and those were the ones that would go on to be the planets. So you would start out with, let me see if I can draw something like it. So basically you'd start out with just a bunch of like dust particles, and then they would combine to form some small like pebbles, and then those would combine to form larger pebbles. So you'd get some stones of decent size, just clumps of rock that are just getting progressively larger, and as those would clump together, you end up with larger and larger chunks, and as you get to a big enough size, those chunks and clumps of rock start to pull themselves into a more circular, spherical type of shape, and so then you end up with planets like the four inner planets that we saw in the solar system. They're all more or less round, and so that's basically the process by which they would have formed. So you'd have started with a ton of like this dust, and then as it starts to clump together, you got some pieces that clump together a little bit faster than others, and so they end up with a stronger gravitational pull because there's more stuff there, and so they have an easier time attracting more stuff, and so you end up with 2, 3, 4 of these clumps of rock that grow faster than anything else around them, and those go on to become the four inner planets of our solar system. Now there's more stuff that we could talk about. Maybe I'll make a video that's like solar system part 2. I haven't decided yet on how deep in detail I want to go, but there's so much that we could talk about, so there's a theory regarding the formation of our moon that involves the existence of a whole other mini planet called a protoplanet. I'll write that out on the screen. Oh, that's a horrible lowercase p. I'm sorry. So a protoplanet. And the second half of that would be planet, but it's all one word. A protoplanet. And that's basically like a mini planet that's not fully formed yet. It's like a baby planet. And so basically you'd have had a baby Earth, so like a proto-Earth, for if you will, and another protoplanet called Theia, Theia. So Theia, which would have been another protoplanet. I'm sorry, it's hard to write with a mouse. So Theia would have been another protoplanet and made of more or less the same stuff as Earth. And basically the two collided, and the baby Earth absorbed Theia, but all the debris that blew off, all the space junk that flew off from the collision, went on to form the moon. So basically you have this proto-Earth right here, and then Theia, which collides with Earth, and a bunch of debris goes flying off from the impact. You just end up with a bunch of space junk that goes flying off in every direction, but the idea is basically that you end up with like a clump of space junk over here, clump of space junk over here. Basically you end up with like a ring of space junk kind of going around, and that all combined to form the moon. So the end picture of this is a larger Earth because it's absorbed that protoplanet, and then you've got the moon out here orbiting the Earth. And so that theory of the formation of the moon involves the existence of a whole other protoplanet. So just because we've got 4 planets in our inner solar system today doesn't mean that we couldn't have had more than 4 in the early solar system, and some of them are just gone through, for one reason or another, that they've vanished. They've been absorbed or been kicked out of the solar system or broke apart or something. But anyway, all the stuff that was left over after the formation of the planets is this space junk, which in the case of the ones that are made out of like rock and metal, like the inner planets, these are called asteroids. And so they orbit together in a ring between the orbits of Mars and Jupiter. So basically you've got, let me see if I can draw this out again, sort of right in the middle here. So we've got the Sun, and then we've got Mercury, Venus, Earth, Mars, and then we've just got this ring that goes around the Sun right here. That's the asteroid belt, and then Jupiter is on the other side of that. So we've got this nice dividing line between the 4 small planets and the bigger planets out in the outer solar system. And that ring of space debris is the asteroid belt. And so basically, that's what it is. It's this ring of space junk, space debris that orbits between Mars and Jupiter. And then the Kuiper belt is a similar thing, but instead of chunks of rock and metal, they are made of ice, and those are what we call comets. And they live in a similar ring, but they're way out in the outer solar system beyond Neptune, beyond the orbit of Neptune. And so it's basically like the outer solar system icy equivalent of the asteroid belt. And then just a final note, there's this thing called the Oort cloud. It's hypothesized in the sense of we haven't actually seen it yet, but it's basically known to be there. It's like a shell of comets. So instead of a ring, it's like, instead of a circle in like 2 dimensions, it's like a ball in 3 dimensions that surrounds the solar system on all sides, made up of comets, and they orbit the Sun at a tremendously huge distance. And basically the end of the Oort cloud is the end of the solar system. When you hit the Oort cloud, you're in interstellar space kind of territory. So it's really far out. That's not going to be a huge part of our discussion beyond this point, but it's worth pointing out that, this is a component of our solar system. There's a lot more than just the 8 major planets and Pluto. So with that said, let's now move on to the outer planets. Now, I understand with the lengths of your guys' classes, this might be a logical place to stop, just with how much time you might have left in class. Unless, of course, you fell short of this last class, in which case now you would just be starting. But anyway, if your class is almost over at the time that you're watching this, this would be a great place to pause, and you can pick up from here next time. But now we're going to jump into our discussion of the outer planets. So here we can see the 4 remaining planets of our solar system. This one here is Jupiter, largest planet in our solar system. This one is Saturn, with the really nice rings. This is Uranus, and this is Neptune. And that marks the end of the solar system in terms of the planets. So let's take a bit of a deep dive into this part of the solar system. So, in contrast to the planets that we saw in the inner solar system, the outer planets are not these tiny balls of rock. They're very large balls of gas. And the gas is basically hydrogen and helium, which are the 2 lightest and the 2 most common elements in the entire universe. So it kind of makes sense that outer planets would have a lot of them, because they're very common elements. In fact, those are the same elements that make up stars. And so we're going to see that when we talk about stars in a lesson or 2. That outer planets are like the mini versions of stars, in that they're made up of hydrogen and helium, but they've got, more layers beneath that, so it's not really fair to call them stars. They don't form the same way. But But you can think of them like stars that didn't get big enough to actually be stars, as a simple way to think about it in terms of the fact that they're made up of hydrogen and helium, just like stars are. As we saw in the pictures earlier on, they are significantly larger than the terrestrial planets, and for good reason, because these 4 planets combined contain 99% of the stuff orbiting the sun. So if you account for the inner planets, so Mercury, Venus, Earth, Mars, and you account for the asteroid belt, which is like millions of these tiny chunks of space debris, maybe billions if you get small enough and you count like little dust particles, and the outer planets, and the Kuiper belt, and the Oort cloud. If you count all of those things together, 99% of the mass is contained in just these 4 planets, and everything else, the inner planets, the asteroid belt, the Kuiper belt, the Oort cloud, make up 1% of the mass of the things orbiting the sun. So basically 1% of the stuff orbiting the sun is contained in the inner planets, the asteroid belt, the Kuiper belt, and the Oort cloud, and the other 99% is contained in these 4 guys right here: Jupiter, Saturn, Uranus, and Neptune. And basically, because they're giant spheres of gas, they are often called gas giants, and that's the term I originally came across. And then as I started to study them in a little bit more detail, going into university and things like that, I saw the term Jovian planets kicked about a little bit more. You don't really need to worry about that, but if you ever happen to come across the term Jovian planet or Jovian planets in like an article that you're reading, chances are they're talking about the gas giants or these outer planets. So the planets that are beyond the asteroid belt and are very big and made of gas. And so again, we've got here the 4 planets. I've included the lengths of their days, and it's interesting that they're all shorter than an Earth day. So they all spin very, very, very fast. But their years are terribly long. The longest year length that we saw for the inner planets was that of Mars, which is about 2 Earth years. It's a bit less than that. It's like 1.8 or 1.9 Earth years, something like that. Jupiter has a year that on Earth would take 12 Earth years for it to be an equivalent period of time. Saturn is even longer. It's 29 and a half basically Earth years for Saturn to go around the sun once. For Uranus, it's even worse. It's 84. And for Neptune, it's 165. So basically, you could have a person that lives to be 84 years old on Earth, but if they were on Uranus, they would live to be 1, maybe. You know, you'd have people that are like almost 1 year old, or they turn 1, or they're 1 and a little bit, and that's it. That's all they ever get. They don't see a second birthday. If you were on Saturn, you know, for me, you know, I wouldn't even be 1 year old if I was on Saturn right now. And so like same for you guys, same for a lot of people watching this, and definitely for a lot of people watching this, chances are you're not even 1 year old on Uranus, which just, if anybody on YouTube just happens to come across this video, chances are they haven't hit their first Uranian birthday yet. And definitely they haven't hit their first Neptunian birthday yet, because that would mean that they're 165 in Earth years. So the years get really, really, really long. Now here's a picture of Jupiter on the left. This is the planet in sort of the way we tend to see it. Here's a cool picture from recent-ish, I think it's a pretty recent photo from the last couple of years or so, that's been taking pictures of Jupiter from its poles, so like from its north and south poles. And I've just included this here just because you can see some patterns in the clouds and the sort of a bluish color to it here that we don't really get to see when we're looking at the planet in this view. You know, if you ask me to color Jupiter on, you know, like to draw Jupiter and color it, I would just color it like orange, white, and brown with a big red blob in the middle. And that's kind of it. I would never think that the polar regions of Jupiter would be bluish in color. But But so that's something really cool. So I just thought, let me include this picture just so you get a view of that. We're going to talk about this in a little while, by the way, this thing. The next planet out is Saturn, and the cool thing with Saturn is that it's the stuff that it's made of is so not dense. Like it's so the planet. If you could put Saturn, this is one of my other favorite facts about space trivia, is that if you could take Saturn and put it in a bathtub that was large enough to hold a planet, and you filled that bathtub with water, and you plopped Saturn into it, and you plopped all the other planets into it, Saturn, even though it's so big, would float because it's less dense than water. So I don't want to say, I was going to say it's light, but it's not light. It's really heavy as a planet, but it's not very dense. It's less dense than water. So if you had a bathtub that was big enough to plop the whole solar system into it, everything else in the solar system would sink. Saturn would float. So that's really cool. And so just to talk about these pictures, here is a picture of Saturn from, I think this is from a few decades ago. And this one down here is more recent. You can see some moons of Saturn in this picture as well. And you can see that the rings are in a different orientation from one picture to the other. So like here, it looks like you're sort of looking at Saturn's like North Pole over here, and this one it looks like, you know, it's different. It's not angled the same way. The rings don't look the same. The shadow's in a different spot, all of that. And that's based on where Saturn is in its orbit, where Earth is in its orbit, and, you know, if Saturn is tilted towards the sun so that it's like summer in the northern hemisphere, it'll look a certain way. If it's tilted the other way and it looks like it's summer in the southern hemisphere, then we'll see the rings look a different way. That it looks like we're looking at the rings from below instead of above. And just to highlight that, here's this double picture of Saturn, one from December 1994, where we can see the rings not quite edge on. We're looking at the rings from like slightly above, it looks like, with Saturn, the planet, obviously right behind it. And then here's May 1995. So Saturn's moved a little bit in its orbit, Earth's moved a little bit in its orbit, but at that point, the rings were like flat. Instead of being able to see the rings the way we normally do, they were just a line that cut across the planet. And so it's really interesting that if you look at pictures of Saturn from different points in time, the rings take on different orientations. They look a little bit different from one picture to another based on where the two planets are, Saturn and Earth, in their orbits, and that decides how the rings will look. Now, next up is Uranus, which is the 7th planet in the solar system. These are all three pictures of the same thing. This is the one that you'll find on Wikipedia. I just find that the color here is a little bit sad. The first picture I ever saw of the planet was this one, which just seems to be a little bit brighter in color, but it's possible that this one was just like an enhanced version of that or something. But either way, these are two pictures of the planet that you might commonly see if you go Googling it. A couple of fun facts about this one is Uranus is the coldest planet in the solar system, and so that's one thing about it that I didn't learn until actually just a few years ago. The first sort of big takeaway that I got about Uranus is that it orbits on its side. So if a planet if a planet like Saturn, for example, if I were to draw it, Saturn might look something like, you know, you've got Saturn here and you've got its rings like this, and so the planet orbits, you know, like this. Similar to Earth, right? With a North Pole up there and a South Pole down there. That's what you'd expect for a planet based on how Earth looks. In the case of Uranus, as you can see here, the rings, these are parts of Uranus's rings, they don't look like they're on the left and right of the planet. They look like they're above and below. And the reason for that is that in the case of this particular planet, and this is the only one in the solar system that's quite like this, and especially with rings to go along with it, is that you've got the planet, but it's tilted on its side, so its rings look like this instead of the way we saw with Saturn. And also that means that when it rotates, you know, like this, instead of rotating the way I just drew for Saturn, that Saturn would rotate maybe more like this. Uranus rotates on its side. It's almost like it rolls. It doesn't actually, it's not actually like it's rolling through space, but that's just the way it spins. Is it's not spinning like a top the way you might expect, like if you were to spin a top, you know, like the little toy. The most of the planets you'd expect to spin the way I've drawn here for a planet like Saturn, but Uranus is tilted all the way over onto its side. And so that's something that I always found very interesting about this planet is, you know, why is that the case? And then it got me thinking when I was younger, you know, why do the planets have different tilts? It looks like Jupiter doesn't have any tilt whatsoever. Earth has a little bit, 23-ish, 23.5 degrees of a tilt to its axis. But then Uranus is 98 degrees. So it's tilted all the way over onto its side and then a few degrees more beyond that. So I just find this really fascinating. So that's sort of like the one big key point that I always have to share about this planet. And then the last planet in the solar system is Neptune. Here again, just like with Uranus, I've got two pictures, one that's sort of in these more dull colors, but this is what you would find on the Wikipedia page for Neptune. And here's what you would find in a lot of articles about Neptune. I guess it's just more attractive coloring of the planet than this one over here. But same idea, same planet. And honestly, looking at the cloud patterns, it looks like exactly the same picture as well, as they've just recolored it. Or it's taken with like a different camera or a different filter or something like that, looking for different information perhaps, so it looks a little different. But yeah, same planet, same picture, more or less. And that's Neptune. Now, let's look at a few interesting things. Some points of interest about the solar system, either in recent decades or currently. So this thing here, this is Europa. It's a moon of Jupiter, and basically it's covered in ice. All of this on the surface is ice, but you can see it's got these huge cracks in the surface, all these brownish lines going through it. So the ice is basically cracked there. And when space probes have gone and flown by Jupiter, the Jovian system as it's called, so Jupiter and its moons, they've made some observations of Europa, and it seems like it's got a lot of liquid water in an ocean below the ice cover. And they've found evidence of it by stuff coming out of the cracks in the ice. So there is a possibility that, provided that it's warm enough, which it seems to be because the liquid water below is liquid, meaning it's warmer than, you know, 0 degrees Celsius or so that it can actually remain a liquid. It might actually be possible that life has developed or could develop in this environment. And so more space probes, more space missions are likely to go and investigate this matter further for Europa. Here's a similar one, same kind of idea, but this is on Enceladus, which is a moon of Saturn. Same thing, we've got like a big icy sheet on the surface of the planet, but it's got these cracks and grooves and maybe signs of something flowing possibly across the surface. I honestly haven't looked into stuff on Enceladus and, you know, research about it in quite some time now, so I'm, you know, a little bit rusty on this, but it's got the same kind of promise as Europa, subsurface ocean, maybe the kinds of stuff that could harbor life. And here you can see how they found evidence of the stuff in the subsurface oceans is that here is the surface of the planet. This right here is, marking the edge of the, not the planet, sorry, the moon, marking the edge of the moon, Enceladus. And then here we've got these plumes of basically geysers. So they're spewing out like water, basically, ice and water out off the surface of the moon. And so if you were to fly a space probe that flies just over the surface of Enceladus, you might be able to collect samples of what's in that stuff and then do a little bit of analysis, and you could figure out maybe is there life here or could there be life here, and so on. And you can go from there to plan out further missions and see if this is something worth studying in detail. So Europa and Enceladus are two candidates for further exploration in the search for life, which I find really interesting because when I was little, all anybody ever talked about was finding life on planets. And then boom, we look at these two moons of planets in the outer solar system. So one, outer solar system, it's cold. Two, these moons have ice coverings, again reinforcing the idea that it's cold. But then boom, subsurface oceans of water with maybe the stuff of life right there, or ready to take hold, possibly. That more work needs to be done, but it's promising in these two to look into it further and just see, is there a chance of finding life here? And actually there's an interesting story to go along with Enceladus, is that some of this research, if I'm remembering correctly, some of the research that led to some of the observations that led to this discovery of Enceladus's potential to harbor life came from a mission called Cassini, which was basically orbiting Saturn and was just hanging around the Saturn system, for like a decade, and it found this amazing stuff out about Enceladus. And unfortunately, it was kind of an emotional moment at the end of Cassini's life, at the end of the space probe's life, is that when it was running out of fuel, they couldn't afford to just leave it there around Saturn, because there was a chance that maybe if it was out of fuel at some point it would crash into Enceladus, and they didn't want to risk contaminating a world that might have life on it with something from Earth. So instead of running the risk of letting that happen, they deliberately flew the probe into Saturn, where it disintegrated in the atmosphere. So it was kind of sad, but it's kind of cool that the probe was able to find out so much useful information about Enceladus and make it promising enough that we couldn't risk crashing the probe into this moon, because there's a chance that there's something there. Not saying there's aliens, I'm not trying to confirm anything, but there's a chance and it's worth studying further. So the next thing here, I don't want to bore you too much. I find a lot of things about astronomy interesting, but this is one of the things that people tend not to be particularly interested by. This is just in case you're interested and you want to do some Googling on your own. There's plenty of research into the rings of Saturn. All I'll tell you for now is that they're not solid rings. They're made out of tiny pieces of ice and dust, basically, that just orbit very close to one another, and so they look like complete solid rings from a distance. And so you can see here, these are some of the moons that actually hang out inside the rings, and here is a picture of one of those moons. I believe it's this one, Daphnis, here. That's actually hanging out right next to the rings on either side, and it's creating this little gap in between and this little wavy pattern in the rings as well. So there's lots of really interesting photos of the moons that hang out right inside the rings and sort of help the rings keep their shape and stuff. So if you're finding this stuff interesting and you want to learn more, or if you've ever just been really fascinated by the rings of Saturn but you didn't know what to do or what to look up shepherd moons, perhaps, if you're hungry for more. I'll write that here. So this shepherd moon. So I'll write it on the screen. And so these are the moons that hang out inside the rings, basically, and keep them in check. So a shepherd moon would be, so this Daphnis, the one on this right-hand side of the screen, would be an example of a shepherd moon. And a couple of interesting things just to, it wouldn't be a complete discussion of the solar system without looking at these two things. So the picture on the left is of the great red spot on Jupiter, and the picture on the right is the great dark spot on Neptune. And both of these are storms, and they are of terrifying size because this great dark spot is about the size of Earth, which is just terrifying to me to think of a storm that's the size of the planet that we live on. And what's even more terrifying to me is that this one is 2 or 3 times bigger than that. So you could fit maybe 2, maybe 3. I've seen the number vary sort of within that range, 2, 2.5, 3 Earths inside just this storm. So I can only imagine what it must be like to be stuck swirling around in these clouds. And the interesting thing is that's different from storms here on Earth is that ever since the Great Red Spot was discovered on Jupiter, which was more than like 300 years ago, it's never gone. It's never disappeared. It's not like a storm that, it comes and it stays for a few days or a few weeks or a few months or a few years. It's been here for literally hundreds of years and it's not going anywhere. So that's really interesting and definitely worth studying further. I always found it really, really interesting myself. But yeah, there's something cool about storms on other planets. And the last picture I have for you right now is regarding volcanism. It says, I think maybe the first confirmed picture of volcanic activity somewhere besides here. And so this right here is a volcanic plume on Io, which is one of the moons of Jupiter. Jupiter's got 4 very large moons. They're called Ganymede, Callisto, Io, and Europa. We've already seen a picture of Europa, and here is Io, and here's some evidence of volcanic activity during a mission that went to Io. So if you're interested in that kind of stuff, feel free to look into it further or ask me questions. But right now I just wanted to, throw a whole bunch of pretty pictures of stuff in space just to show you, that there's a lot out there. So, we've seen lots of really interesting information about the planets, and I know this lesson is already over an hour long. Hopefully you guys have split this across 2 classes, but there's lots of interesting stuff there. For me, it was as simple as the length of day and length of a year on the different planets that captivated my interest. But when I was like maybe 4 years old or so, maybe even 3 years old, I was looking at pictures of the planets in like library books and anywhere I could see them. I was so fascinated by this stuff, so I thought it would be very fitting for our solar system lesson to basically be looking at pictures of the planets, because that's what got me into it in the first place. And here I am 20 years later studying this stuff, and I absolutely love it. So there's lots of really interesting stuff. There's plenty more that we could talk about, and maybe I will talk about in a future video, which is like the formation of the solar system, the future of the solar system, and we'll touch on these kinds of subjects as we go on. But there's so many other things. You could talk about moons, you could talk about rings of the planets, you could talk about how many moons the outer planets have, because Earth's got 1, Mars has 2, but Jupiter and Saturn have in excess of like 70 moons each. It's ridiculous. And Uranus, if I remember correctly, has like 27, and Neptune has I'm not remembering exactly, but like it's like over a dozen as well, and they've each got like five big ones or something. Like there are a lot of things out there worth studying. You could look at pictures of the planets, and you can look at pictures of the planets that are taken with different lenses that highlight different things. Like this one highlights the geology, or this one highlights the magnetic fields, or this one highlights this. And there's so much interesting stuff out there. So if you ever want to learn more about any of it, let me know and I will get you that information that you're looking for. Basically, suffice it to say that there is plenty of interesting information about the planets out there. As for how we found all of this stuff, I don't want to bore you with, using a bunch of like technical language to talk about how these kinds of missions are developed or the kinds of instruments that they might use. But if you're interested in reading up about them, you can absolutely go and Google the different kinds of missions or projects that led to the exploration of various objects in the solar system, with some particular emphasis on the Moon and Mars, especially in recent years with, like the Curiosity rover, for example, being like a fan favorite, but also, missions to visit the other planets, even if it wasn't landing on them, with like flyby missions of the outer planets. Like Voyager 2 is like my favorite space mission ever is the Voyager program, and specifically Voyager 2, because it flew past Jupiter and then Saturn and then Uranus and then Neptune all in one go. And so you can just imagine the kinds of math that had to go into calculating that, this is where we're going to send the probe, and this is where Jupiter's going to be, and then we're going to take pictures of Jupiter, and then it's going to get flung off in another direction towards Saturn, and then you do the same calculation 3 more times so that Voyager 2 could visit all 4 of the planets in one go. And there's so much interesting information out there, but there are plenty of other missions, and honestly, I haven't looked into them as much as I would like to. There's so many. There's the Pioneer missions, the Mariner missions, Messenger, Luna, the Venera probes, which were, I believe, a Soviet project to get to Venus, and they managed to land a probe on Venus, take a picture, and then the probe got fried by the intense heat and maybe also squashed by the atmospheric pressure. But yeah, so there's so much interesting stuff out there. And with some of the big players in space exploration, including the US and the Soviet Union from the days of the space race, with also other space agencies like the European Space Agency being a big one, also other countries getting involved like India, and China as well in recent years, also Japan and a few others. But basically there are a bunch of countries that are getting into space research these days, but sort of the big players of the previous century, of the 20th century, were the US and the USSR, as they had that space race to get the first man into space, the first satellite. Those were both Soviet accomplishments. They got their first into space. They got a person into space. They got the first. I think they also got the first woman into space, and the first dog into space. I think those were all things that the Soviets did first. But then obviously the U.S. got to the moon first. So, those two in their competition to be the first to things in space, they led us to a manned mission to the moon, and maybe in the future, in the not so distant future, we might have a manned mission to Mars. Exciting times in space exploration. And it should be emphasized that space exploration is totally an ongoing endeavor. It's not like we've figured out everything. I know when I was growing up, I would look in my books about the solar system, and I felt really bad that I felt really disheartened and dejected. I was like, all of these things were explored like 30 years ago. And now obviously when I was like 6 years old, 30 years felt like a really long time. So I was like, okay, well, like I missed it by like a lot. But I felt kind of bummed out that I'd missed this era of space exploration, but it's totally still ongoing. Now, obviously there are some things that our generation, your generation, has just missed, with like the first man in space, this guy, Yuri Gagarin. Um, and all of that stuff from the space race, but there's some ongoing stuff. This object wasn't even discovered until like maybe 8 years ago, I think. Um, and it's gone from not being in existence to having one of those sort of those names that don't make any sense for objects found in space. When I first heard of this object, it was called 2014 MU69. It was called this 2014 MU69 was the name of this object, and since then it's been found, it's been photographed, it's been visited by a space probe called New Horizons, and it reached this object like 3 years ago. So, you know, this exploration of the solar system is totally and completely an ongoing endeavor. It's not all figured out, and if one of you is interested in pursuing this kind of stuff, you know, you absolutely can. You absolutely can. So it should be mentioned that within our solar system, no life has been confirmed to exist or to ever have existed on any other planet or moon in the solar system, but it does remain a possibility. The search for signs of life, present or past, is absolutely something that's going on in astronomy, astrobiology these days. It does remain a possibility that life could exist out there within our solar system. Within the universe, I'm a strong believer that it does. Again, no concrete evidence for it. I just kind of thinking about the possibilities. I feel like, you know, it has to exist out there. But in terms of looking for evidence, there are some promising places like those moons in the outer solar system, like Europa and Enceladus, which we talked about. And there are some suggestions that life on Earth might have actually come to be thanks to, you know, like microbes, like bacteria arriving from like a comet or an asteroid, or the debris from like a collision between two other objects in the solar system might have been what brought the seed of life onto Earth. That hasn't been verified. It's just an idea that's out there. So, you know, maybe Earth is the only planet that has life now, but maybe it didn't originate here. Maybe it came here from something else, like an asteroid or a comet. But of course, that's speculation. So I felt it's necessary to comment on, you know, the search for life within our solar system, but no amazing news as of right now in terms of an actual discovery. There's just, I personally find it amazing news to have these promising places like in the outer solar system to be able to look for signs of life, present or past, in these amazingly different and distant places out in the solar system. It's really cool. But now to end off this lesson, and honestly, with how long it is, it's entirely possible that you guys would like to split this into 3 classes instead of 2. I'm going to talk about Pluto. This is, I think, something that has to be addressed in any lesson on the solar system these days. And it's something I promised myself I would address anytime I'm trying to teach anyone about the solar system. So, Pluto, everyone's favorite dwarf planet. So it was discovered, here's just a little bit of history, it was discovered back in 1930 by a man named Clyde Tombaugh at the Lowell Observatory. This is the guy he was working for. It's so far away from the sun that it would take, it does take 248 years for Pluto to go around the sun one time. So, you know, I'm not even like 10% of the way there to turning 1 on Pluto. It's like it takes so long to orbit the sun, and in fact, it takes so long to orbit the sun that it hasn't even completed a full orbit since it was discovered, because it hasn't even been 100 years since Pluto was discovered. And it was originally believed to have just one moon, which was a reasonably large moon given the size of the planet. It's a really small planet. And that moon is called Charon. But more recently, some of which at least some of which, maybe all of them, but at least some of them were discovered after a space probe had been launched in the direction of Pluto to go and visit it and take some pictures. And over the course of that mission, they were like, hey, there's more stuff orbiting Pluto. That's kind of cool. And so it turns out that Pluto actually has 5 moons, which definitely surprised me, given that Pluto was, while it was a planet, it was the smallest planet in the solar system. So you would have expected it to have 1 moon tops, and probably not much else. But it does have 5 moons. Also, a bit of a fun fact about Pluto and Charon is that they're sometimes considered to be part of what they call a binary system, because they orbit each other instead of one orbiting the other. So what that means is that instead of having let me find a place to draw this. So if instead of having Pluto here and Charon orbiting Pluto like this, instead of that, what we have is Pluto here and Charon here, and they both kind of orbit each other like this. But what's actually happening is they're both orbiting some common point in space, and this happens for anything, any two objects. So if you've got like even the sun and Earth, they're both orbiting a common point in space. The thing is, it's just usually that point in space is inside the heavier object. So like if you have the sun and Earth, sure, they're both orbiting a common point in space, but that point in space is inside the sun. So effectively, Earth is orbiting the sun. But in the case of Pluto, that's not what happens. Pluto and Charon are orbiting a point in space that is outside Pluto. So for that reason, sometimes it's called like a binary system, but that's just again another like sort of fun piece of trivia. And Pluto and Charon and the rest of the moons were explored by the New Horizons space probe in 2015, which is not very long ago. It's the same mission that found that that weirdly shaped object a slide or two back, Ultima Thule. And this New Horizons probe was launched in 2006, so it took a while to actually reach Pluto. It took 9.5 years to actually get to Pluto. But it got there. It took some awesome pictures. I'll show you one of those pictures, maybe 2 of those pictures a little bit later. But first we have to address the elephant in the room. Why was Pluto demoted? Why did it lose its status as a planet? So, I'm going to explain the sort of official reason, I guess. Except I'm not a fan of the official reason. So then I'm going to explain sort of why I'm okay with Pluto not being a planet anymore. So when I was in school, I was taught that Pluto was a planet, at least for a little while, because they changed the definition in 2006. So while I was in school, I saw that change from 9 planets in the solar system to 8 planets in the solar system. And the books that I used to read when I started getting into astronomy as a really little kid, they all said 9 planets, because that's what was true at the time. But so anyway, Pluto has been demoted ever since 2006. It's not called a planet anymore. It's called a dwarf planet. And so here's the thing. Basically, there's this organization called the International Astronomical Union, and they're like, I don't know, you could call them like the rule makers of stuff in astronomy. It doesn't matter too much about like who they are and what they do, but basically they've got the authority on this matter. And basically what happened was Pluto was discovered back in 1930, and they were like, oh cool, new planet. Sweet, 9th planet in the solar system. They originally thought it was about the size of Neptune, but when they got better and better measurements from their observations, they realized it's actually very, very small. But, you know, just because it's really small and really far away and has a really weird orbit, those weren't really good enough reasons to not let it be a planet. So basically, here's the thing, is that a bunch of the planets, the rest of the planets, in fact, so if you've got the sun here, the planets' orbits look like this, and they kind of all look like this. They're like flat and they're circular-ish. Obviously, they don't look circular when I'm drawing them on the screen like this. But so basically, the planet's orbits look like that. And then Pluto's looks like this, which is just kind of weird. Now, obviously, that's not a good enough reason to just stop something from being a planet. That's like discriminating against orbits or something. So basically, there was something a little bit weird about Pluto. It was really small, it was really far away, and it's on this really weird orbit that the rest of the planets don't seem to have. So it was always kind of like a bit different from the rest of the planets, but that wasn't a good enough reason to change the definition. Anyway, in more recent decades, astronomers started to discover other objects in the outer solar system that were like beyond the orbit of Neptune, and also really small and, icy objects, basically kind of resembling Pluto, and maybe on weird orbits as well, probably on weird orbits as well. So basically it was like, Pluto's not alone out there. We've got some extra buddies. But the problem is Pluto is already so small that if you're finding more stuff out there that's even smaller than Pluto, maybe those things just aren't planets. Maybe they're just asteroids or comets or something, space junk that you're finding way out in the outer solar system, right? Because not everything out there is a planet, right? We've got the asteroid belt. It's full of this like space junk, but they aren't all planets, right? So maybe we were just finding these tiny chunks of like ice, and maybe they were all just comets or whatever that we were finding way out in deep space. But then they started to find more and more and more of these, and they thought, it's getting a little uncomfortable to keep calling Pluto a planet, but it's okay as long as we don't find anything bigger than Pluto, because then, if you find something bigger than Pluto, either you need to say we've found a 10th planet, or you need to cut both out of the list and say, you know what, these are all something else. We actually only have 8 planets, and Pluto's actually this other thing. So once they found something larger, and they did, they found, I think in 2005, maybe, I think they found an object, might not have been 2005, might have been earlier. But anyway, relatively recently, within the last 20-30 years, they found an object larger than Pluto, or at least more massive than Pluto. I think they thought it would be larger, and then it turned out to actually just be a little bit smaller, but it is more massive. There's more stuff in this other object called Eris, E-R-I-S. And so the thing with Eris is that because it was more massive than Pluto and originally thought to be larger than Pluto, it was like, okay, now we got to decide, is Pluto a planet and Eris is a planet, or are neither of these two objects planets, and they're both something else, some weird deep space objects that we didn't have a name for yet? And so the International Astronomical Union, basically, they were sitting there and they asked themselves, like, okay, well, what is a planet? And then they all kind of looked at each other, and it's like, we don't have an actual like dictionary definition for what a planet is. We just kind of called these things planets because of how they moved in the sky, and that's it. That's what the Greeks did. They called Mercury, Venus, Mars, Jupiter, Saturn, the Moon, and the Sun planets. Incidentally, that's why we've got 7 days in the week, is that we originally had those as the 7 planets: Mercury, Venus, Mars, Jupiter, Saturn, the Moon, and the Sun. Obviously, since then, the Moon has been not classified as a planet. It's because it's, not. The Sun is not a planet, it's a star. And Earth is a planet, which wasn't in the list of planets originally. But anyway, I digress. Basically, this IAU, International Astronomical Union, they realized that they don't have a proper definition of a planet. So they came up with one, and this was in 2005, 2006, that they came up with this new definition, and that's the one that you can see on the screen here. It says, a planet is a celestial body that is in orbit around the Sun. Okay, it orbits the Sun, goes around the Sun, has sufficient mass to assume hydrostatic equilibrium. So that's basically, it has enough stuff to be round, is basically what it means. Because if something is too small and not massive enough, it'll end up being like just like kind of whatever shape. It doesn't have to end up being round like a planet or a star. If you get small enough, they end up kind of being whatever shape they want. And the third point is that it's cleared the neighborhood around its orbit. So that basically means that the planet orbits the star and nothing else orbits the star from, a really similar orbit. So like if you've got, let me see if I can draw this out. So suppose you've got the sun here, and then you've got a planet that's got an orbit that looks like this, let's say. Orbit that looks like that goes around the sun. So that's fine, but what if you've got like a tiny piece of space junk that's got an orbit that looks like this? That's like really similar. It's like, okay, that's all right. But what if you've got another one, another space debris thing, piece of space junk that's got an orbit that looks like that? I mean, what if you've got another one that orbits like this? So basically they're saying is that if you've got a bunch of other junk that has an orbit that's really similar to yours, you're not a planet. You don't count as a planet. If you've got a whole bunch of other stuff that orbits in basically the same space as you need to be the dominant gravitational body, or whatever, something like that is what they call it. You need to be the dominant gravitational body in your orbit, and basically what that means is you need to either absorb these other things in your orbit or kick them out of their orbits. One way or another. So that's the definition. Here's the problem. A lot of people weren't happy with this definition. A lot of astronomers in particular. But the general public were not happy to lose Pluto as a planet. It was, everybody's favorite as like the runt of the litter and the one that was different and stuff. But I'm also not a fan of this definition, and not for that runt of the litter kind of reason. I've got problems with this definition itself, which we'll visit now. So, a couple of problems here. The top half of the slide is exactly the same as the previous one. But so, problem. It says a planet is a celestial body that is in orbit around the sun, which means that only if you orbit our sun, our star, could you possibly be a planet. If there's something that looks exactly like Earth and it's the same mass and it's the same size, but it orbits a different star somewhere else in the galaxy or somewhere else in the universe, by this definition, that is not a planet. And I think that is a horrible definition, or that it's a horrible criterion to have as a definition for a planet, because something that looks like Earth and has the same size as Earth and the same mass and the same gravitational pull and moons or rings or whatever, but it orbits a different star, it should totally still be considered a planet. So anyway, that's an oversight on the part of the definition, and I find that awful in the sense of it sounds like you made that definition so quickly that you didn't catch your mistake of saying the sun instead of a star. So it feels like it was all rushed, and I already don't like it just because it was supposed to be, we're setting this definition properly, it's going to be written into stone. Then do it right, don't make a mistake like this. The second point is this one about being round. Assume hydrostatic equilibrium. The problem with this is, if you look at the bottom of the slide, Mercury fails to meet this criterion. So that's not good. Because if these are the criteria of planets, then you should probably keep the other 8 planets that aren't being contested about whether or not they're planets, right? But anyway, Mercury apparently fails to meet criteria number 2. It's not close enough to being round, even though it did look that way in the pictures. I guess if you go through all the observations and the math and stuff, I guess it's not round enough. As for the third point about clearing the neighborhood around its orbit, 4 planets in our solar system fail that criterion. Earth has about, I was on the Wikipedia page to double check the numbers, Earth has about 10,000 buddies in and around its orbit, like little asteroids that orbit around where Earth's orbit is. There are about 10,000 of them, and for Jupiter there are about 100,000 of them that orbit in a path similar to the one Jupiter takes around the sun. And Mars and Neptune also have something similar. So all 4 of those planets fail criterion number 3. And you can find this on the Wikipedia page, because I've definitely got my own issues with these points. but there something like Mercury failing criteria number 2. I didn't know that until I went and did some research on this. Um, but then I found after that, oh, it's right on the Wikipedia page. So if you want to go and see, you know, definition of a planet, you'll see the criticisms of a planet, and it'll include things like this. So Earth, Jupiter, Mars, and Neptune fail criteria number 3, point number 3, about clearing the neighborhood. Mercury fails point number 2. And other objects in space. So exoplanets, which are planets that orbit other stars, they're not included, right? Because a planet has to be in orbit around the sun, apparently, right? So exoplanets don't count. Rogue planets, which are planets that maybe used to orbit a star, but for some gravitational reason or another have been ejected from their orbit. So now they don't have a star that they orbit, they just float through space. But they, you know, it might look like Earth and have the same mass, it might even have a moon with it, but if it doesn't orbit a star, it doesn't count as a planet. So that doesn't, well, at least under this definition. So then exoplanets aren't included. Rogue planets aren't included, and brown dwarfs, they're already a little bit fuzzy as sort of blurring the line between planet and very small star. But same thing, they're just basically these other sort of somewhat exotic types of objects out in space that just aren't included or aren't, you know, properly nailed down inside or outside the definition of what constitutes a planet. My biggest problems with this one, just on a personal level, nothing against the IAU for this particularly, to me it just gives me the impression of the first point being a little bit rushed in that it says the sun instead of a star, and the third one to me just looks like it's kind of like a specific to Pluto kind of point that, like, you know, if you asked me to define what a planet is, I wouldn't have thought about, well, what other stuff is in its orbit? And it seems like only because this was the point of contention with Pluto, it's like, hey, we found a planet, but now it has a bunch of other stuff around it, so we need to address that in our definition of a planet. Like, it feels to me like it was tailored very specifically to the Pluto situation, which that might not be true. It's just that to me it kind of looks that way. And so I just don't really like the way that it's worded, at least. But even aside from that, the fact that 4 planets in the solar system fail to meet that criterion, like, it's maybe that should be rethought. Because otherwise, you know, in trying to define whether or not Pluto is or isn't a planet, you're throwing the planet status of 5 other planets, 5 other objects into contention, right? Mercury, Earth, Mars, Jupiter, and Neptune all have failed to meet one point or another in this list, as well as all the objects not in our solar system because they don't orbit our sun. So, you know, there are definitely problems with this definition, but unfortunately this is the definition that was used to reclassify Pluto as a dwarf planet. And so, you know, that's what Pluto is now. Is it's classified as a dwarf planet. That being said, I do think Pluto has been rightfully reclassified from planet to dwarf planet, but for the wrong reasons. So we've already talked about the wrong reasons, right, on the previous slide. And that's not to say they're, you know, actually wrong. That's me giving my personal opinion, is that I think that they could have gone about that process a bit better. But anyway, the thing is, I can see it being done because this reclassification business of planets has happened before. In the case of an object known as Ceres, which is a dwarf planet that is in the asteroid belt, and you've probably never heard of it because it's not considered a planet. Thing is, Ceres was discovered in 1801, so, you know, 200 years ago, and it was considered a planet at the time, and it's actually large enough to be round, so that's pretty cool. If you go look up a picture of Ceres, you'll see that it looks like it totally should be a planet just by looking at it. So it was considered a planet when it was found, and probably rightfully so at the time. But then they just started to discover other objects in nearby orbits. So they found an object called Pallas in 1802, and they found an object called Vesta in 1807, and they started to find more and more of these little objects that, these objects were all kind of really similar to each other, but really different from the planets on both sides. You've got Mars on one side, you've got Jupiter on the other side, and then you've got these like 4, 5, 6, 7, 8, who knows how many that they ended up actually finding in here before they reclassified. But you have Ceres, you have Pallas, you have Vesta. They're all really small, they all orbit in kind of the same area, and as you start to find more and more of these, you start to think, it's like, well, maybe all these things between Mars and Jupiter aren't planets. Maybe they're all something else. Maybe, possibly. And so then, you find enough of these and you thought, you know what? We're not going to call them planets. We're going to call them something else. We're going to call them asteroids. And so actually, if you see here, Ceres and Pallas and Vesta, and I believe another one called Juno, if I'm remembering correctly, were all considered planets when they were discovered. And only when you found enough of them that you realize, oh, these are all more similar to each other than they are to the rest of the planets. Let's reclassify them all. And so they were all reclassified from planets to asteroids. And Ceres ended up being reclassified to a dwarf planet with that new definition of a planet on the previous slide, just like Pluto got reclassified to a dwarf planet. But basically, Ceres was a planet, Pallas was a planet, Vesta was a planet, probably Juno was also a planet, and then they all got reclassified, all because they being the scientists, the astronomers of that time, they had found enough planets or enough of these objects between Mars and Jupiter that they realized, these are all too similar to each other and too different from the stuff on both sides of them. So they reclassified them as asteroids, and maybe there was some pushback from the public in 1810, 1820, I don't know. But nowadays we're all totally fine with it, right? And in fact, most of us have never heard of these objects, Ceres, Pallas, Vesta. So I think it's kind of a similar situation for Pluto, is that, they found one, Pluto. It's a pretty big one. When you look at the objects that are way out past the orbit of Neptune, Pluto is one of the biggest ones, if not still the biggest one that's been found. One of the most massive ones. Obviously, Eris is a little bit more massive, but it's one of the biggest ones. It's one of the closest ones in the Kuiper Belt. It's one of the most massive ones. So it makes sense that we found it first. But when your technology improves and then you start to find more and more and more, now maybe you're getting into the territory of what we saw with Ceres in the 1800s, that, you find this thing, it's like, oh, it's a planet, but then it turns out you only called it a planet because you found that one first, and then once you started to find a whole bunch more, you realized, oh, it's not a planet, it's actually something else. Let's call it that something else. So to me, this is all a personal opinion. This slide and the last slide is at least partially a personal opinion on the last slide, because there was some stuff that I got off Wikipedia there. But this slide is my personal opinions, that I think Pluto has been reclassified for the right, it deserved to be reclassified, but they did it for the wrong reasons. And that's just basically, I just don't like the wording of the definition. I do think reclassifying it was right, and for me that reason is basically that I think it paints a more accurate picture of the solar system. If you wanted to make a simple model of the solar system where you ignore the asteroids, you ignore the comets, you ignore the Oort cloud, you ignore the moons of the planets, and you just want to look at, this is the sun and these are the planets, I think the most accurate picture that you could paint of the solar system in that case is with these 8 big planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Now, of course, that could be biased. Somebody from 300 years ago would want Ceres and Pallas and Vesta in there probably, right? And there'll be a lot of people today that would want Pluto in there. And so for me, basically, whenever I have this kind of a conversation with somebody, I tell them, either you should count Pluto as a planet along with Ceres and Eris, and maybe some of the other ones that are out there as well, like Sedna and Haumea and other objects way out in the deep solar system or in the asteroid belt. So either you should call Pluto a planet with these other ones as well. So instead of having 9 planets, we have like 12 or 13, or you give Pluto the axe and we have just 8. So that's just my personal opinion. Obviously, you guys, this isn't going to be something that you're like tested on or whatever. Um, but yeah, so that's my take on the Pluto situation. I wanted to explain it in detail just because, this is a really big topic that comes up anytime people talk about the solar system these days. And especially for me, being somebody who studies this kind of stuff, they'll ask me, it's like, oh, what do you think about Pluto? Do you think they did it right? Do you think they, you know, why did they do it? And so this is my take. So hopefully you guys kind of understand where I'm coming from, and hopefully you guys kind of understand where the IAU was also coming from with the way everything has gone on with this situation. And here, just to round out this lesson, which is now a resounding 100 minutes long, I'm so sorry for that, but it'll keep you busy for a couple of weeks, I guess. Here's a picture of Pluto that was taken in 2015 by the New Horizons space probe. I watched this picture along with a bunch of others that came in basically, as soon as it came out, I saw it. Because I was just staring at like NASA's page and refreshing the page, waiting for news to come in, and they brought in this picture. You can see there's like a nice, like, even like a heart shape right here in the surface of Pluto, which of course didn't make it any easier for people to say goodbye to Pluto as a planet. And but there's a lot of interesting science that's being done. So regardless of whether Pluto is a planet or not, there's lots of interesting stuff to learn about it, and I absolutely encourage all of you to look into it and try and learn what you can about Pluto without letting the planet not planet debate kind of get in the way of that, because there's a lot of amazing science going on in the outer solar system, and learning about the stuff that's out there and its history and its future. And don't let the naming of whether it's a planet or a dwarf planet or something else, don't let that bog you down. So there's a picture of Pluto, and there's a picture of Pluto and its largest moon, Charon. This was also taken by New Horizons. You can see that same heart shape here on Pluto. So this picture is like rotated 90 degrees relative to the one that we saw on the previous page. And there's Charon up there. You can see it's reasonably large compared to Pluto. And so they orbit a common point. I don't know exactly where it is. It's probably somewhere around here that Pluto orbits around this, and Charon orbits around it as well. And there's probably a common point somewhere out here in space between the two. Just to wrap up really quickly, this isn't the most important thing in the world, but I'm going to just briefly mention it, is that there are some scientists that believe that there might be yet another planet way out in the outer solar system. And by planet, I mean like large planet, not Pluto-sized, but like Neptune-sized, maybe. Way out in the outer solar system. And it could be something that is found in the next couple of decades, if it's actually there and if the evidence mounts. There might be some indirect evidence. So indirect evidence meaning not like pictures of a planet out there, but like seeing how other things in space respond to a massive object that might exist in that area. So it's like if you're watching how Pluto moves, and you see that Pluto's not moving exactly the way it's supposed to, then that might hint to there being something more massive hiding behind it that's pulling on Pluto or something. So that's not happening with Pluto, at least as far as I know, but it is happening with other objects, is that their orbits are pointing towards the possibility of the existence of another planet, a new ninth planet elsewhere in the deep solar system. And the use of this kind of indirect evidence has happened before with the discovery of the planet Neptune, because basically the planet Uranus was not moving the way it was supposed to. Basically, it was getting a gravitational tug. It was getting pulled forward and then held back by something hiding in the shadows in deep space. And so from the laws of physics that we had, and we were looking at, I say we like I say we as though I was a part of it. I absolutely wasn't. This was like 200 years ago, 150 years ago. Basically, the scientists of the time, they were looking at the predicted movement of Uranus, and they were looking at what actually happened, and they said these two aren't lining up, but they would line up. The equations, the math, all the predictions would line up if there was another planet out there pulling on Uranus. So they pointed their telescopes there, and they found Neptune. And so this has happened before, that they've used indirect evidence of how one object moves to deduce the existence of another. So it is possible that there's a ninth planet hiding out there. I don't know. We probably won't know for a few decades, couple of decades at least. But something to keep your eyes peeled for on any space news that you'd like to follow. So that's it for this lesson. We're at a 1 hour 45 minutes. So basically, I hope you guys have split this into like 3 classes or something. But yeah. This is just a picture to leave you guys for this video. This is obviously a picture of Pluto that I encountered somewhere on the internet shortly after, or actually maybe shortly before the flyby, because they just started to get these close-up shots of Pluto, and people obviously noticed that heart right away, and so they started to make pictures like this. So thought I'd leave you with that. Especially given all the discussion about Pluto in this lesson. So anyway, I hope you guys learned a lot and enjoyed the content in this lesson, and I really hope you split it across like 3 classes. But anyway, I will leave you with that. If you have any questions, let me know in the comments, or send me an email or a message on social media or Discord or something, and I will get back to you. If not, then I will see you all in the next video. Have a good one.